Ferrite suppression cores are frequency-dependent devices used in the attenuation of high-frequency noise. They are available in a wide variety of form factors that can be clamped on cables, surface or through-hole mounted on printed circuit boards, and machined into unique geometries for custom applications. There are two factors to consider when choosing a ferrite suppression core. First, it's important to know the frequency range you need to attenuate. Our FR75 material is best used to attenuate frequencies in the range of 150 kHz to 30 MHz. FR43, 44, and 46 are mid-range suppressors good for frequencies up to 300 MHz. And for higher frequencies up to 1 GHz, FR61 is the best choice. It's also important to know your cable size. Ferrite suppression cores are available in a wide range of inner diameters to fit almost any possible cable. Once the proper ferrite material for the specific suppression application has been decided, picking the required ferrite core is the next stop in solving the EMI problem. The core contribution to the impedance is expressed in the formula noted below. From this formula, it can be seen that the impedance is proportional to the square of the number of turns and the core geometry shown by the core factor C1. The effect of squaring the number of turns dramatically increases the impedance and thereby the suppression. Also, as a result of the formula is the contribution of the core height. Doubling the length or height of the core will double the impedance. Larger cores will provide more impedance and thereby offer more suppression. We are now ready to calculate the attenuation of a ferrite suppression core using the following formula. If we know the load impedance, source impedance, and the impedance of the ferrite core, we can solve for attenuation in decibels. Fair-Rite Corporation's 17th edition catalog will be consulted for the core impedance. Now let's use the formula to predict the attenuation of Fair-Rite Snap-it core 047516 4181 at 1.5 MHz using 3 turns. From Fair-Rite's 17th edition catalog, we can see that at 1.5 MHz, the circuit will see approximately 800 ohms of impedance. We'll use a 50 ohm source and load impedance, and we can see that the formula predicts 19 decibels of attenuation. Next, we will move on to the lab to try and verify our prediction. Let's try to verify the calculation we made earlier by actually measuring what effect ferrite has on a circuit. So let's review our setup. Here we have a current transformer. Here's our signal generator that will put out a 1.5 megahertz signal in the square wave form. We're terminating this with a 50 ohm load. Above it, we'll be measuring the output waveform on our spectrum analyzer. Here you'll see the fundamental frequency of 1.5 megahertz. You'll also see harmonics that extend out far into the megahertz range. Currently, without ferrite, we're measuring the output at approximately 36 decibels. Now let's see what effect ferrite has on attenuating the unwanted signal. We know from our previous discussions, to attenuate a 1.5 megahertz signal, our FR75 material would work best. Here I've inserted a core with 3 passes through the aperture. Now let's take a look at the spectrum analyzer and see what effect it's had. We can see that the spikes are definitely reduced, and at 1.5 megahertz, the signal strength is now approximately 17 decibels, indicating that we've achieved approximately 18 dB difference by inserting the core in the circuit. So let's go over what we've learned in this short course. First, suppression cores are frequency-dependent devices. It's important to know the frequency you want to attenuate so you can pick the right ferrite material. Larger and longer cores offer more attenuation, and it's possible to calculate how much attenuation a given core will give.